So today how to build a DIY battery analyzer, a battery capacity meter. A lot of people were asking me to make a video about this one, and out of hundreds of schematics I published, this one is definitely the most commonly constructed one by my viewers. But instead of making a video about this one, I decided to build one more. For me it will be very handy to have two, so I can test two batteries at the same time, and you will see the process of building it. And I will do some small modifications, but really just small, because after 10 years of using this one, there's really not much I would change on it. And yes, I have built it exactly 10 years ago. Now let's take a peek inside of it, how it looks, and then let's start building another. It has a microcontroller in it, one op-amp, some potentiometers for calibration, the current sensing shunt, some voltage sensing resistors, the display and its resistors, the crystal, some capacitors, and a power supply with 7805. And this LED indicates the battery is discharging, and when the LED turns off, the battery is discharged, and you can read its capacity in milliamp hours or amp hours, and its energy in watt hours. Here's the fuse for case something shorted, and the control buttons on the front panel, and that's basically it. There's really not much to it. And of course, to discharge the battery, it's using a power transistor on a heat sink. This basically dissipates the energy, and it's controlled by the op-amp. There is basically a feedback loop from the current sensing resistor, so it draws the current you set. Here's the voltage on the battery. Here's the energy in watt hours. You can read after discharging the battery the capacity in amp hours, the time of discharging, and the discharging current from 10 milliamps to 2.56 amps. And here's the final voltage where it shuts down. And back to the actual voltage of the battery. The mode button basically goes through 6 screens, and to set it you have the plus and minus buttons, and the long press of the minus button doubles as a reset to reset the previous measurement and measure another battery, and the long press of the mode button starts the discharging. The LED indicates it's discharging, but of course now there is no battery, so it shuts down immediately. Because basically with no battery, the voltage is 0, so it's below the minimum. And it has a power supply with 7805, so it can run on anything from about 8 volts to about 30 volts. I'm powering it using my DIY bench power supply. I'm choosing a box for the new one. You can buy various project boxes like these, with screws and a cover. And of course this time let's be lazy. Instead of making a window in the box and putting a foggy glass into it, let's just use a box which is already semi-transparent, like this one, or with a red cover like this, which of course requires a red display then. And this one is too thin, I guess it might not fit. This one is the right thickness, but it's a little bit small. I was thinking this one would actually match with this heat sink, but why make it small when you can make it bigger? I have this box which sort of matches with the heat sink. Cut it like this and it will have a bigger heat sink to be able to dissipate more heat. It's again semi-transparent. This would work really well with a red display. The minimum final voltage is 0.8 volts now. I will modify it to 0.75. Not that any device is going to run at this voltage, but anyway, just to be able to test the batteries the way they're tested in the datasheet. And this requires me to change this resistor from 0.24 ohms to 0.22 ohms, which is a much more common value anyway. And of course I will use some more accurate resistor than this one this time. And also the calibration potentiometers are quite coarse. I basically move them just a little bit and it makes a big difference. So I will make the calibration a bit more fine. And here is the schematic of the new one. Of course it's going to be on my website and I will put a link to it in the description. And some slight modifications compared to the old one. Here's the current sensing resistor, a little bit changed. The battery has 2 wires going to the positive. One is for the voltage sensing and one is for the discharging via the transistor. Now the fuse is in the way of the transistor, not in the way of the voltage sensing, so its voltage drop is not influencing it. The fuse is there for case the transistor shorted or the current regulation feedback failed. It prevents it from drawing excessive or short circuit current from the battery and causing a fire. I'm changing the values of the resistors and potentiometers, and these two to make the current and voltage adjustment more fine. And instead of using just one pin to control the LED and shut down the discharging, I'm using 2 separate pins. I'm also thinking about using a different type of op-amp. This is an old one which is no longer made. Of course I have a lot of old stock from the 90s or early 2000s, but because a lot of viewers are asking me how to replace it, I might actually build it with a different type to test it. Because this circuit is quite particular about the op-amp. It has to be able to reliably operate at 5 volts. The inputs also have to be rail-to-rail, at least able to operate down to 0 with a non-symmetrical supply voltage. It has to have a low offset and an offset null potentiometer, because the offset is quite critical when setting low discharging currents, because then the voltage on this current sensing resistor is quite low. Of course, I might change certain things here, so the final schematic will be on my website. This is still just a temporary schematic of the new version. It can be used to measure the capacity of almost all batteries: nickel metal hydride, nickel cadmium, lithium ion, lithium iron phosphate. I definitely plan to try the new sodium ion batteries. It can also test lead acid batteries, and also battery packs with more cells in series, as long as the total voltage is not more than 20 volts. And of course the power dissipated in the transistor is the current times the voltage, and the transistor has to be able to handle this power dissipation, as well as its heat sink. And of course you might say in various test loads they tend to use a Darlington transistor instead of a MOSFET, and the reason for that is that Darlington transistors are more suitable to operate in a linear region than MOSFETs. But the reason I'm using a MOSFET is to be able to discharge the batteries down to about 0.75 or 0.8 volts. And this voltage still has to cover the drop on the transistor plus the voltage drop on the current sensing resistor. And of course the saturation voltage of a Darlington transistor might be too high for this. The transistor has to be able to operate with the battery voltage minus the voltage drop on this current sensing resistor, and at the maximum current it can end up with less than 0.2 volts on it, which is not possible with a bipolar transistor, let alone a Darlington. That's why I'm using a MOSFET. And of course ideally you're using a MOSFET which is specified for a DC operation in its forward biased safe operating area in its datasheet. If the SOA doesn't specify DC, the transistor might not be suitable for it. And of course this thing can also test non-rechargeable batteries, but in such case the test is destructive, obviously. And the modifications in the program are just very few. One is that this pin is actually copying what this pin does, and as the voltage goes down to 0.75 instead of 0.8 volts, and that's it so far. And again, as the voltage reference for the voltage measurement, it's using the voltage from 7805 voltage regulator, 5 volts, going in through the supply pins. And because the supply voltage is well regulated, also the output pin voltage is regulated basically, and so it can use a pulse width modulation to generate the reference voltage for the current regulating circuit. It's basically a constant current circuit with an adjustable reference. This pin is pulse width modulated and it goes via a filter and a resistive divider, producing a DC voltage on this capacitor, and the voltage drop of this current sensing resistor is basically compared with this reference voltage, and the gate of the transistor is regulated accordingly. And there's this negative feedback via this capacitor for stability, and the shutdown is basically by pulling this inverting input up by this pin of the microcontroller. And the voltage sensing on the battery basically uses a resistive divider of this resistor and this resistor with an adjustment potentiometer, and it goes into this analog to digital converter input of the microcontroller. And of course somebody might be screaming, why not calibrate it digitally instead of using the potentiometers? Well, this makes the program simpler, also turning a potentiometer is simpler, and also digital calibration compromises the resolution typically. If you want it digital you can do it in your version, of course. But things are typically designed different way when you're making just 1 or 2 pieces from how they're designed when you plan a factory to spit millions of them. Of course, for mass production, a digital calibration would make more sense. When something's designed different than you're used to in consumer products, it doesn't mean it's a wrong design. This is just meant for 1 piece at a time manual production. And of course I also forgot to mention that the output voltage swing of the op-amp is critical. In some low voltage op-amps, especially bipolar ones, it's quite low. In a low state the voltage still can be about 1 volt at the output, and in a high state it can be 3 or 4 volts. In some bipolar op-amps like this one the swing is non-symmetrical. It goes down to 0.1 volt or 0.2 volts, let's say, but up to, let's say, only 3.5 volts, which is much farther from the supply rail, which is 5 volts. And of course when it's low, it has to be low enough to turn the MOSFET completely off, and when it's high, it has to be enough to turn the MOSFET reliably on. And of course the voltage drop on this current sensing resistor is subtracted from the gate to source voltage. So if the minimum output voltage of the op-amp in a high state is, let's say, 3.5 volts, the transistor has to reliably turn on at barely 3 volts gate to source. So you have to use a logic MOSFET with a very sensitive gate. And of course the drain to source voltage rating of these logic MOSFETs is typically 30, at most 40 volts. But we don't need more voltage rating here. And now the heatsink is cut to the size of the box, and it will be mounted on it using these. I've chosen a universal board for it, and let's cut it to size. Amazing! How did you expect me to manufacture the board? Putting the components on the board, even more components on the board. And of course the board for the buttons. Somebody donated these nice buttons to me, so thanks for the donation. How much solder you can possibly use to solder a couple buttons. And the holes for the buttons, and the buttons will be screwed onto it. That's it. Even more components on the board. Now just about all the components are on the board, and the button has got a cable with a connector that plugs into here. And as the current sensing shunt, I put two parallel 2 series resistors, which keeps the original resistance but spreads the heat better. And red silver is 0.22 ohms. You can put it in my component marking online calculator, and that's the resistor. We can also use the other calculator, the calculator. We can put the resistance into it and the maximum current through it. And calculate the voltage drop on it and the power dissipation. 1.44 watts. One of the 4 resistors would be enough. Now a transistor has to go on the heatsink. Scissors for the bearing, of course. Let's give it some isolation pad. Do you prefer mica, silicone, aluminum oxide, aluminum nitrate? This is massively excessive, just like the current sensing resistors, but let's see how much more I can over-engineer it. Aluminum nitrate is probably the most thermally conductive isolation pad you can get. Beryllium oxide is probably a little bit more conductive than this thermally, but there's no modern TO220 shaped version of it. I'm not actually sure what this thing is made of, but it would be surely a good idea to grind it and sniff it. But of course I don't need it because I stopped watching news a very long time ago. And I guess the only thing even more thermally conductive, which is not electrically conductive, is a diamond. Now the transistor's on the heatsink, of course, with the plastic insulation ring. The heatsink compound is always so pleasant to work with. Now let's make a hole in the box and pull the wires in. Now let's demonstrate the pulse width modulation of the constant current source. Reference voltage. Turning it on. And it's pulse width modulating at about 31 kHz, and let's increase the duty cycle, and you can see it averages to a higher voltage when the duty cycle is higher. And of course the channels are not the same scale. The channel 1 yellow is the pulse width generator output, and the blue, the channel 2, is the reference voltage. And these are the pins of the crystal. And this is 2 out of 4 display multiplex pins. These go to the common anodes. And of course the pulse width modulation on the analog oscilloscope can't be missing. I put the op-amp into it, and let's see what happens when I don't put the stability capacitor into it. At some settings the feedback is oscillating. This is 100 milliamps, 150, 170, and it's oscillating. 250 milliamps. Without the capacitor, the feedback oscillates at about 100 to 150 kHz. When I add enough capacitance, it disappears. I'm comparing how sensitive the gate is of various transistors, basically how much gate voltage is necessary for the transistor to pass 2.56 amps with 2.5 volts drain to source. And the transistor I was testing actually requires more than I expected. There's not as much headroom as I want, given the op-amp high state output voltage and the voltage drop on the current sensing resistor. The transistor I was using in the first version required just 2.51 volts, and now I'm testing this one, which requires about the same gate voltage, reasonably low, and it has a lower junction to case thermal resistance and it's quite cheap. But of course there is the option, if you don't have a very sensitive gate transistor, to power the op-amp from the voltage before the 7805 regulator. Then you have much more voltage available for the gate, and you could use MOSFETs that are not logic level. But I decided to power it from the 7805, so it works in more controlled conditions. I also plan to test this type of transistor from Alpha Omega Semiconductor. They seem to make quite good transistors. I ordered this one and I will test it when it arrives. Now I'm testing this one at 20 volts and 2 amps, which is 40 watts. Absolutely baking the hell out of it, and it's not failing after over 2 hours. It appears to be good at running in the linear region. Here's it on the heatsink dissipating 40 watts, and some thermal imaging. And the transistor close up. And the current sensing resistors on the board, and way too many test probes everywhere. The rest of the board is cool. Maybe a little bit heat from the 7805 regulator. It's shiny actually, reflective in infrared. And the total consumption of the battery analyzer is about 27 milliamps. About 9 volts go into the 7805 regulator, and of course the more voltage the hotter it gets. And this is it tested at 2 amps, 20 volts. Now the op-amp is the same type as in the old version, but I might try different types when they arrive. And of course the display is not very readable without the red filter. I plan to test these two transistors. They're quite affordable and they have quite a low junction to case thermal resistance. And DC specified safe operating area. I tested that as the stability capacitor 330 pico is not enough, but 470 pico is enough. But of course for it to have enough headroom I put 10 nano in it anyway. It works even with 100 nano, but then the response of the current regulation might be slow. So I'm using a 10 nano capacitor in it. Now the calibration. The voltage measurement calibration is very simple. There is just one potentiometer for it. And you just turn it so it shows the same voltage as an accurate multimeter. And the current calibration is a bit trickier. It has two potentiometers for it. You start with setting the offset potentiometer to the middle of the scale. Then you set it to the maximum current, 2.56 amps, and you're using a battery or a power supply capable of more than 2.56 amps. And you adjust the current potentiometer, so the actual current is also 2.56 amps. And of course the current meter is in series with the positive or the negative battery terminal. And then you go to the lowest current, 0.01 amps. You set the offset potentiometer, so it's actually 10 milliamps or 0.01 amps. And that's about it. And you might have to reiterate a couple times. You set it back to the maximum current and adjust the current potentiometer. And then you go back to the minimum current and adjust the offset potentiometer. And that's because both potentiometers actually influence both ends of the range. But the current potentiometer mostly influences it at the top of the range, and the offset potentiometer influences it mostly at the bottom of the range. That's why you're setting the offset at the minimum current, and the current potentiometer at the maximum current. And I gave it one extra function. You can actually put this jumper in, and it sets it to double the range. Now it's up to 5.12 amps in steps of 0.02, and the minimum is 0.02. I did this because somebody was asking for it. To build this version, you basically put the jumper in place and also half the resistance of the current sensing shunt to 0.11 or 0.1 ohms, and then you calibrate it around it. And of course I tested the feedback is not oscillating, in basically all combinations of voltages and currents. And in the active mode with the LED lit, it draws about 28.6 milliamps from the power supply. So it's all working, I just have to screw it all together. But before this, I want to test several more different types of op-amps and several more different types of transistors in it. Because everybody will be asking me if they can use a different op-amp or a different transistor. I will test several and give you a list of transistors and op-amps you can use in it. But I don't want to recommend anything I didn't test. So I will wait for them to arrive and test them. And of course the video is getting bloody long, so I will try it in a different episode. And in that episode I can also explain how to read the datasheets of op-amps. A lot of beginners don't know what to look for in a datasheet, and they're asking me if they can use the 741 op-amp. Absolutely hell no. In my designs I always try to use the most common, easily available and cheap component. So if I use some special, unusual or expensive component, it means it's necessary. And of course the final schematic and the program for the microcontroller will be on my website. So that's it about finished, other than waiting for the fuse holder. Other types of op-amps and power transistors in another video. And if you're asking about the accuracy of it, well, there are 3 factors. The time measurement, the voltage measurement, and the current regulation. Using a crystal, the time is measured more accurately than anything else here. And the voltage measurement, well, the voltage measurement matters for the termination voltage, but the discharge curve of most batteries at the end is quite steep. So even a big difference in the termination voltage causes just a small difference in the measured capacity. So the voltage measurement isn't critical either here. So the accuracy of the capacity measurement mostly depends on the accuracy of the constant current circuit. And of course this was bloody laborious to develop, build and program. So please consider using the thanks button and supporting me accordingly to the value you received from this video. Also consider becoming my patron on Patreon and subscribing. And big thanks to all of you who already support me. This channel couldn't exist without you.